Okay, everyone, we're back. Fourth week of our lessons here. Okay, so we are going to be looking at solving polynomial equations, and we're going to be looking at some more problems, okay? But first, as usual, we are going to quickly review what we did in the last week. Here is the polynomial function. Can you pause the video and do a quick sketch of this? Okay, so I'm assuming you finished it. Let's quickly look at this. Remember to graph polynomial functions. What we need to do first is to find out all the x-intercepts, which means we need to factor first. Okay, so to find out its factors, remember we need to use the rational root theorem. So we look at the factors of the constant divided by the factors of the leading coefficients. And I always try one first, regardless of the question. And I know if I plug in 1, this will actually give me a 0. Okay, so which means I can do a long division. So that's 2, 3, -6, -5, and 6. I can put in I can put in 1 here. That's 2. 2 added together is 5. That's -1 times -1. That's -6 times -6 is -6 here. Added together is a 0. So I know x minus 1 is a factor. And then after that, I will get 2x cubed plus 5x squared minus x minus 6. Okay, so then let's see. I think I can plug in 1 again and get another 0. So if I plug in 1 again, this will give me a 0 as well, which means I can divide this by x minus 1. So 2, 5, -1, -6, bring down the 2, times 2, add them together, times 7, add them together, times 6, add them together. And then that means, again, I have another x minus 1 as my factor. So what I have left with is 2x squared plus 7x plus 6. Okay, and I can easily factor this. This would be 2x x plus 2 and then plus 3 here. Yeah, that will work. So my equation, I guess, my function, my polynomial function then became x minus 1 squared, because that's one of them here, second one here. And then we have 2x plus 3 and x plus 2 as well. So I can find my x-intercepts by simply looking at this factor form. I know I would have an x-intercept at 1. I would have an x-intercept at -1.5. Okay, again, -1.5 plug in here will give me a 0. And -2. Okay, -2, -2 plus 2 is 0. I can also find my y-intercept very easily. Recall, y-intercept for the polynomial function is always just a constant term. So that's right here, 6. Okay, so that's my y-intercept. So now, okay, so I found all of my intercepts. Now I need to look at the properties of this polynomial function. I see that the highest exponent is a 4, so I know this is an even degree. Okay, even degree. And I know the leading coefficient is positive. So if even degree and the leading coefficient is being positive, means it's going to behave like a parabola, meaning it's going to go from quadrant 2 to quadrant 1. Okay, so now we are going to go through our very first x-intercept at -2. The multiplicity at that root is 1, right? Remember, it's x plus 2 to the power of 1. So the multiplicity of that root is 1, which means it's just going to go through. The next root is -1.5, and again, the exponent here, the multiplicity of that root is also 1. So what that means is that it's going to go through the first x-intercept and then go through the second x-intercept, just like that. It's going to go to the top, come back down through the y-intercept, and then as it approaches the last x-intercept here, I know the multiplicity at that root is 2. If it's a 2, remember, if it's an even number for the that particular root, if the multiplicity is an even number for that root, remember, it's going to touch and bounce back. So it's going to go towards it, touches it, and goes back. And I guess then you go up like this. Okay, so it's a W-shape graph. Okay, hopefully you remember that. So again, let me just quickly review. Anytime you see even number multiplicity, it's going to be touch and bounce. If the multiplicity of a root is 1, it's just going to go through, right, straight through. If the multiplicity at the particular root is 3, 5, 7, 9, and so on, it's going to have this kind of curve, right? It's going to go down fast, slows down, and then slowly going through, and then drops quite fast, like that, okay? Or if it's going up, same thing, it's going to go up fast, and then slow down at that root, and then goes up slowly, and then goes up quickly, like that, okay? So that's what's happening at the root if the multiplicity is 3, 5, 7, and so on. If it's 1, it just goes through. If it's a 2, it will touch and bounce. Okay, so that's the review for 1.4. Hopefully that wasn't too bad. Solving polynomial equations is very, very similar to what we just did. Really, all we needed to do is to factor, and then we basically are done, because solving polynomial equations is just like finding the roots, right? Finding the x-intercepts of the graph. So all you have to do is factor. So I think you should be able to do it. I will give you a minute, pause the video, try this, and see if you can do it. Okay, so I'm assuming again you finished it. For this question, I can see that every single term has x in it, so I know right away I can factor the x. So I get 6x cubed minus 7x squared minus 14x plus 8 equals 0. So now this is a cubic function, so again we need to use the rational root theorem. Let's see, does 1 work in this case? I guess 1 doesn't really work. How about 2? Does 2 work? 2 doesn't work either, hey? 2... Oh, wait a minute. 2, 28, 20, 56, 2, 8, 40. Oh, 2 does work. Okay, perfect. So if I plug in 2 in here, if I plug in 2 into x, this does give me 0. So that means I can actually do a long division for 6x cubed minus 7x squared minus 14x plus 8. And I will put 2 here. This is 6, 12, add them together is a 5, times them, add them together is negative 4, times them, add them together is 0. So this is going to be x times, again, 2 is the one that works, so x minus 2, times 6x squared plus 5x minus 4 equals 0. Now this is just a regular quadratic that we can actually factor quite easily. Okay, so let's see. I think it's going to be 3x and 2x. I'm just guessing and checking here. 4, it's probably 4 and 1. No, 2 and 2. Or not as easily as I thought. I think it's plus 4 and minus 1 here. 3, negative 3. Yep, that's right, that works. Okay, so 3 times 2 is 6. 3 times negative 1 is negative 3. 4 times 2 is 8. 8 plus negative 3 is 5. Yeah, that's perfect. And 4 times negative 1 is negative 4. Okay, so, well, then I'm basically done, right? So I'm just looking at every single set of brackets, I guess. For the first one, what makes x 0? Well, if x is 0, then it's 0. What makes this bracket 0? If x is 2, that will make it 0. This one's going to be negative 4 out of 3. And this one is going to be 1/2. So there you go, 4 answers. That's how you solve polynomial equations. Okay, factor it. That's it. And then basically you're looking for your x-intercepts. It's the same concept. Okay. If you have any questions, again, you can pause the video, think about it, maybe rewatch this part again. But if you don't have any questions, then we are going to move on to the word problems. Okay, let's take a look. It says a cardboard box company makes boxes with no tops using a cardboard that is 67 centimeters long and 46 centimeters wide. By cutting out a square from each of the four corners and bending up the sides, we form the box, right? So like this. If we have a cardboard, it looks like this. If we cut and this is 67 by 46 centimeters. If we cut a little square at each corner, and of course these four squares have to be the same size, and then you fall along the edges, it forms a box with top open, right? There's no top. Okay, so we are going to write a polynomial function to represent the volume. Now remember, volume is, so in general, volume, this is going to be a rectangular box, a rectangular prism. So volume is equal to length times width times height. Now we don't know how much we are cutting, right? We don't know the length and we don't know how long these side lengths are for the cutouts. So I'm going to say that this is x. And if that's x, this would also be x, right? So all these sides that we're cutting out will be length of x. Okay, now if this is x and this is x, now what would the rest be then? Well, we had 46, right? We had 46 in the first place. We're cutting out this piece, which is x. We're cutting out this piece, which is x. So this, whatever that's left, would just be 46, that was the total, minus the two x's that we're cutting out, right? So here, our new width, so I'm going to call this v of x now, okay? So this is v of x. The volume in terms of x is going to be 46 minus 2x. Well, I guess that's my width. It doesn't really matter. My length, well, it was 67 before, because we're cutting out this x and we're cutting out this x. So now whatever that's left is 67, take away the two x's that we're cutting out. Okay, hopefully that makes sense to you, right? We're cutting out x on either side, so we're taking out two x's. So now the total, or the remaining length, would be 67 minus 2x. And the height is simply however much we are cutting out, so we are bending that amount, right? So bending up. So the height would just be x. Okay, so there you go. Write a polynomial function to represent the volume, and that's it. That's all you have to do, okay? You don't actually need to multiply this out. That's perfect. Okay, so part B, it says we want to graph the function and what is the domain. Okay, now before we actually graph this, I want you to think about the domain first. Now, when we talk about domain, we need to think about its restriction. Obviously, if it's a polynomial function, the domain should be all real numbers. Now, because we have a context, right? It's a word problem, so there's a context to this question here. So we need to think about what restrictions we have. Well, because we're cutting out things, right? The cardboard box, x has to be bigger than 0, right? There's no way x is less than 0, because we can't really cut negatives. So x has to be greater than 0. Okay, it cannot be equal to 0 either, otherwise it's not a box. So that's the minimum. Is there a maximum? It turns out there is a maximum, right? If you think about it, if I cut, let's say 25, if x is 25, then if that's 25 here and that's 25 here, then in total that's 50. But 50 is already longer than my entire side length, right? My entire side length was 46. So really the biggest size that you can cut is just slightly below 23, okay? Because this is 46 and you're cutting the same amount on either end. So the biggest amount you can cut is just slightly less than 23. Because if you cut 23, that's the halfway point, and you're basically cutting the cardboard in half. That's not a box, right? Just cut it in half. So 23 would be the smallest. Now, we consider this side and not this side because this is the shorter side, right? 46 is the shorter side. So the maximum has to be there, right? I mean, if you think about it, if you consider length here, the maximum you can cut there is 33.5. Sure, you can cut 33 there, but you can't, right? 33 here and 33 here is fine, but if you put 33 here and 33 here, then that's not okay. So we look at the shorter side, right? So our domain, so if you combine these two restrictions together, our domain is this. X has to be between 0 and 23 and not equal to 0 or 23. Okay, so that's our domain. This is our domain. Okay, now we are actually going to use decimals to graph this, but I mean, just to, we can actually graph this quite easily now because we know how polynomial graphs work. We are going to look at our x-intercept, and based on that, our x-intercept is 0. Based on this, as I mentioned earlier, it will be 33.5. So let me just say 33.5 is here. And based on that, the x-intercept will be 23. So let's say somewhere here. Okay, we'll use decimals in a second, but we will actually try to sketch it first, just to see what that looks like. Now this is a cubic function. You can see that's x times x times x. So this is cubic function because it's degree of 3. So this is odd degree. Is this positive or negative leading coefficient? Well, that's negative 2x times negative 2x, which will give us positive 4x squared, and then times x. So it actually will give us 4x cubed, right? Positive 4x cubed. So the leading coefficient is actually positive. So if it's positive and odd degree, it's going to behave like a linear function and going upwards, right? So from quadrant 3 to quadrant 1. Okay, like that, right? So now we're gonna do a quick sketch. Now every single root has a multiplicity of 1, so we're just gonna go right straight through. Okay, so it will look like this, something like this. Okay, now this would be the graph if there were no restriction, but there was a restriction, and it has to be between 0 and 23. So really our graph, the only part that we need to consider is this portion, right? The rest we don't really care because it's not gonna happen, right? Because it's not possible. So really it looks something like that. That's the only part of the graph that we need to consider. Okay, so we are going to look at decimals and see what looks like, because we're actually going to use that to answer part C. You know what? Let's actually answer look at question part C first. It says, to the nearest cubic centimeter, what is the maximum volume of the box? What size of square should be cut out to create a box with this volume? And to the nearest tenth of a centimeter, what are the dimensions of the box? So let's actually graph this. So here is decimals, and let me just enter in the equation, the function there. So I think it was 60. What is it? 67? I forgot. 67 minus 2x. Oh, 67 minus 2x times, what was it? I can't remember. 46 minus 2x. What the? Okay. 46 minus 2x, and then times x. Graph that. And I guess I should put y equals. And then I am going to change the setting of the graph. As you can see, that's not what it should look like. We can zoom out a little bit, I guess. Okay. Okay, and then now we're gonna zoom in. There we go. Looks much better. Okay, there we go. If you look at the entire picture, it looks something like this, right? There we go. Looks something like that, and that's what we predicted to look like earlier, right? It looks like that. Okay, so that's our graph, and again, we are only gonna consider the middle portion, okay, from 0 to 23. Well, you can see here, there's the x-intercept of 23, that's the x-intercept of 33.5, and x-intercept of 0. The question says, what is the maximum volume? Now remember, our y value, that's our v, okay? The y value represents the volume. So if we want to find the maximum volume, simply we just need to click the maximum point for this graph. Again, we only consider between 0 and 23, so the right-hand side we don't need to consider. We only consider this portion. So that is our maximum volume. The maximum volume is 12,348.414. So the maximum volume. So for now, you can only do this by graph. If you take calculus in the future, then you'll be able to actually calculate this by hand. Okay, 12,348 point, what is it? 414. 414. The unit was cubic centimeter. Okay, what size of the square should we cut? Well, the x value here is 8.941. So we need to cut 8.941 centimeter to achieve maximum volume, or to achieve maximum. That sounds weird. To get maximum volume. Okay, and to the nearest tenth of a centimeter, what are the dimensions of the box? Okay, so to the nearest cubic centimeter, I guess. So this is just 1, 2, 3, 4, 8 then. Cubic centimeter. What are the dimensions? Well, so the dimensions are simply length times width times height. So then it's going to be 46 minus 2x. So 46 minus, we want to get to the nearest tenth. So 2 times 8.941. That's our length, or this is our width really. And I'm going to put this into a calculator and see what we get here. That's 46 minus 2 times 8.941, which is 28.1 centimeter. And the length will be 67 minus 2 times 8.941, which is, let's see. Let me clear this. Where's my clear button on my car? Whatever. Okay, so this is 67 minus 2 times 8.941, and this is 49.2 centimeter. Oh, 49.1, sorry. And the height would just be 8.9 centimeter. Okay, so there's our dimension. Okay, last example, and then we're done. So here, again, if you have any questions, maybe you can watch it again, or you can ask me during office hour, of course. Okay, example 3, a 1 liter rectangular container of a milk carton measures 10 centimeter by 5 centimeter by 20 centimeter. The manufacturer would like to redesign, or would like to design a 2 liter milk carton with each dimension increased by the same amount. Okay, what are the dimensions of this larger container? Okay, so basically, well, same thing really. We have, let's say here's our milk carton, and this was 10 by 5 by 20. We are going to increase each side length by the same amount and effectively double the size. So we don't know how much we're increasing by, so then we are going to say that we're going to add x to it. We're going to add x we're going to add x to each side. So the volume, we know the volume is now 2000, right? Because that's what we wanted. And this is going to be 20 plus x times 5 plus x times 10 plus x. Okay. So then you can, again, this is not going to turn out nicely if we solve algebraically. So we're going to graph this on Desmos and see what it looks like. Okay, so 25 and 10. Okay, so let's go back to Desmos. I'm going to create a different graph. Okay, I'm going to hide that one. So y equals, we have bracket 10 plus x times 20 plus x times 5 plus x. Okay, like that. Let me just double check. 25 and 10. 25 and 10. Good. Now, what we want is we want to find out where this graph intersects with 2000. So basically, we're looking at this point right here. Now, we can't really just click and then get exactly 2000. It's going to be very difficult. So what we can do is we can type in another function and we say y equal to 2000. That will create a horizontal line. Then we can simply click on where they intersect. Then you can see that will give us a very nice point. You can see when x is 2.296, the y value will be 2000. So if we increased each side by 2.296 centimeters, then the volume will become 2000. Okay, and that's really all you have to do. So we need to increase each side by 2.296 centimeters. So what are the dimensions of the larger container? It's gonna be 5 plus 2.296, so 7.296 centimeters by 10 plus 2.296, so that's 12.296 centimeter by 20 plus that, so 20.296 centimeter. This would be the size of the new larger container. That will be 2000 cubic centimeter or 2-liter milk carton. Okay, that's it for today or for this week. Here are the questions that you are encouraged to do. I think 3 to 11 are must-dos, and number 12 slightly more challenging, but I think you should probably be able to do as well. Okay, good luck. Let me know if you have any questions. Bye.